thanks for joining this talk. So thanks for the introduction. Probably all know me the first day of training. So today I'll talk about, I change the topic a little bit. Initially it's called text-dominant mesh generator for image-based simulations, and then I switch from text to voxel-dominant. So you see why we changed it to voxel, because I thought voxel base is more appropriate for this talk. So yes, I'm from Cranfield University, lecture there, and since last 3 years time, we're developing this meshing technology initially for our own pipelines, and then we start to find some interesting results, and we thought, okay, probably we can form a spin-out companies out of this. So we got supported from Cranfield University, and we formed a spin-out company called Voxel. Later we'll see why we call it Voxel. So yes, this we generate this kind of voxel dominant mesh, and this we actually present our company logo. So overview of the conditional packages we have developed. You have seen this slide in the Monday. So we developed basically two parts. One is the pre-processing part, we call it short mesh. We'll spend most of the time today. The other one is the voxel-dominant, voxel-based solver. So actually, during my PhD study or during postdoc, we spent many time on developing this voxel-based solver because it's very efficient. And like say lattice Boltzmann, front-end-based or Boltzmann transport solver. So always voxel-based, because we can use in condition grid to do very efficient looping. Previously, I know we use also like FT-based solver to accelerate the solver, the different type of nice conditioners, etc. So, and that's the motivations why we developing this voxel-based meshing technology. We would like to stay in a voxel-based transition, but adding a little bit on the boundary side, so we call it shell. So that's why we're developing this shell technology, and it can be directly imported to OpenFOAM at this stage, and to run it in OpenFOAM. I'll showing this in the Monday. So this is the overviews of things we have developed. We have this voxel-based solver. It's very efficient, and different parallel computing with different situations. And this is current the things we have developed. But it's all voxel-based. But later we can think about how to have hybrid solvers to hybrid with the boundaries or the shells outside. So I highly emphasize that the lattice Boltzmann solver we have developed so far I think it's called IBSim-4i. It's running in different platforms, GPUs, CPUs, and also cross platform distributed memory as well. So it's actually received many stars in GitHub, and actually most stars repos in LBM community. So feel free to use it. And now let's move into the meshing part. So what is the problem of the meshing for the imaging simulation? This is a snapshot from a paper. Doing this simulations with a commercial software. I can't mention name. But after the image simulation, this is a structural problem. This is using biomechanical engineering. So they start to using implant some driven portfolios, and after they do stress analysis, after compute this and automatically run the mesh, I noticed that there's this all unstructured mesh, and in this corner part we have very tiny meshes. If we want to capture the small features, we need to push the element size very high. Also, it causes, because the mesh size goes very large, it takes a long time to compute. And sometimes we have some local stresses which is not real in this coordinates, and that is the main problem we can solve. So our solution is here. We provided a voxel domain mesh. This example showing the Stanford bunny and normally used in computer graphics. So there are several parts. So you can see that after we doing the meshes, this we call the bookshelf format. So inside is all voxel based. Outside are very good quality unstructured mixed unstructured mesh, including the deformed schedule, the text mesh, schedule mesh, and pyramids. It makes type of meshes. And another thing is if we want to share the data, which we only save the shell parts. If you want to share it saves a great amount of memory and I/O. There's the main problem of if you upload any meshes to the HPC, to the cloud computing, the server actually can be parallelized very well. People start doing that, but the mesh is a big problem. If they upload a big amount of meshes to the main nodes, so there's memory not there, and they do the domain decomposition, etc. There's a lot more pain there. So if we're doing that, we only save like 1.5% of the total amount of mesh. Depends on the applications, of course. But do internal flow, external flow, or internal stresses, we'll see. So this is the typical things we have compared with in-place surfaces, point cloud, voxel-based, or 3D meshes. And overall, we have compared different things. Of course, our virtual mesh is fast because we save the shell parts. It's very good accuracy. The graphics we can do it very graphic. And industrial solver can be directly solved. We can use different front-end based or front-end anything you like. In terms of rendering, it's also very fast. So because it only rendered polygons outside, so it's extremely efficient in graphic cards, and in terms of memory, it's also good. So it's very also. I was going to talk about neural network for rendered part, so I would say it's also very good. Let's look at this memory saving or storage saving. I have a small box there with a Stanford bunny inside. We do two cases. One is the inner mesh, one is outer mesh. This compare the different usage of the memory or storage we have used there. So in the bottom line, there's two lines, which depends on the meshes. Because if you're solving outside or inside, the memory or I/O cost is more or less same because at the same time because they have that's the meshes for two sides, right? So it's more or less same. But if it goes up, but if compared with the standard mesh generator, I can see there's a huge saving. It's around 2 magnitude of saving of the data. Then another thing I should mention is because compared with voxel, compared with the unstructured mesh, if you have the same number of nodes and do the unstructured mesh, the unstructured mesh will be at least five times more compared to the voxel mesh. If it is how it's split, that's how you can do the unstructured stuff. So that's the main advantage actually, saving doing some I/Os and it provides good quality of mesh. And if it is voxel based, so the mesh quality will be perfect, right? At least in the side. Because we know time how to do this in the shell parts. And we will have the automatic workflows we have shown on the Monday. After the image segmentation, we can generate the mesh, and the boundary conditions as well, and directly copy them into open form, and then we can solve the problem. So everything is in the currently I would say is we designed it for open form solver, but can be used for other stuff. So it's been developed for the last 3 years, but in this April actually we went to the there's a meshing conference in Amsterdam. As we turned this meshing context competing with other commercial softwares. There's all the commercial there. So this is basically they provided it was held in Amsterdam, so it provided meals or smash. So it's very this showing parts of mesh everything. You can see that if it depends on the geometry, if it is something like a volume take a lot of amount of, if there's not too much small features, our voxel or hex can be takes like 99% or 97% of the whole mesh. So it increase, I would say, increase the speed up the computational time, but also save a lot of memories and that things. And you have to see other parts. Everything is very good pattern, especially for small shells. We also have two elements to form to generate this plate. So that looks perfect. And let's look at this compare with the one of the leading unstructured mesh generators. This is the one we have which is different. They're both coming from there. And this that's the one is one by the commercial product. And the one is our product, very patents. And similar things happen in this type of mesh. Very nice, unstructured, great. And in the red one, it is their commercial product. And you can, I know we are all experts in traditional mechanics. You can understand the benefits of using this element in terms of doing stress analysis. Save a lot of time. And and next one, let's keep one slide about the voxel meshes and functional mesh. Basically, if we take out the shell, this is what's left there. So we only see shells, we see this one. So it's pretty another one. So there's a few applications there. The first one is we have already used this in some commercial some of our pipelines. This one showing design a new aluminum reactors for some companies. So you can do this if you have STL, you can do this with hex mesh. But I will emphasize that the good things why I bring this because I'm not sure whether you can see that. The edges of these cylinders is very well preserved. So that is the key. That's a very good point of this mesh generator. Because if you use other buildings hex mesh, you have some small. You can already preserve these edges in a cylinder. This is what shown in the cylinder. The edges can be preserved. And this is another example where we do some marine energy application. This is the wind turbine, floating wind turbine foundation. This is solving this one with polymer fluids and oversetting mesh. So you can see this is showing the capability of doing a depth mesh of different layers. If you go, we have very good matching of joints. And we have three transition layers between adaptive mesh and also so we have the mesh adaptivity. And the novelty part of our is we don't need the box. We don't need the huge box. If you see the mesh in the left side, is basically we can set up a growth length and then so save some time if the structure if there's something wrong with the structure. And this is another example is about the photon reactor. So we're doing the flow over the photon reactor. This is for the relation view. So this relation view is computed by digits. Also based on framework. We have not done into the CFD simulation. The big tricky part is the related part is about the small bubble over there. This part is targeted to capture in the mesh, but in this example shown the very good capture small features like small things. And this another one is about the. I'll finish the very soon. It's about the wind turbine application. The challenging part of this here is the trailing edge part. It's very hard to preserve trailing edge, but yeah, this is now we are able to do that. If you're doing with semi-hack mesh, doing some wind turbine solution with a very thin edge, that's be a big pain for all the mesh. Pre-announcement. We have online versions in next month, so it's free to use. It's small. This is our online version. We already put this online, but we have spent some time how to fix out the database. So yeah, it looks like this. You drag files into the online version, directly generates the mesh for you. That is one thing. And future work, we're going to do some boundary data generation based on applications and the multi-processor implementation. So we are doing right now it's one processor, but we have some tri version. We have two processors. Processors working, which looks great. And also there's another important feature is we want to use also accelerated with source overs. Because if we separate this into two parts, I would say it's great. It will be a great acceleration of the solver. So thank you for your attention. So this is my LinkedIn page. There's two emails. One is about my Cranfield email. One is about company emails. You can add me on LinkedIn if you like. We are open to collaborations, and yeah, and of course we are trying to make more fundings. If you're interested, yes, please talk with me more after this talk. So any questions so far? One. Time for one.